Okay, we are discussing mechanical vibration. The last class we discussed about the free vibration. The free vibration without damping. The free vibration means after giving the initial disturbance to the system, no further disturbance given to the system. System vibrate freely, that's called the free vibration. The damping means there's no energy dissipation method associated with the vibration. So then these things, actually the damping method also we discussed in last lecture. The three different types of damping: the viscous damping, friction damping, and hysteretic damping. These things we discussed in the last lecture in detail. Then the today's lecture is focusing to discuss free vibration with viscous damping. The free vibration with viscous damping. That means the free vibration, there's initial disturbance is given. That means initial energy transferring activity is given. Then the system vibrate freely without further disturbance to the system. So then they are also associated with energy dissipation method. Okay. Then in this situation, how system behave, we are going to study in this lecture. Actually, there's three different situations, three different behaviors we can identify, called the overdamp, underdamp, and critical damping situations. These three situations we are going to discuss in detail in this lecture. Okay. Then let's continue to today's theory. Okay. In this lecture, we are going to discuss about the free vibration with viscous damping. It also called damp free vibration. Damp free vibration. Damp free vibration. So what it means? Actually, the first let me illustrate that this. What is the free vibration? So what is the free vibration? In the last lecture, we discussed in detail about the free vibration. The vibration. Let me summarize what we did in last class. In the free vibration, what happened? Actually, we discussed free vibration without damping in last class. This kind of system we considered. In a free vibration, there's an initial energy transferring activity. That means we are giving the kinetic energy to the M mass, or we are giving the potential energy to the spring. That means we are compressing the spring, then releasing, or we are giving certain velocity to the M mass. There's a two method to give the energy for this system, this kind of system. The kinetic energy as the form of kinetic energy, as the form of potential energy. Okay. Then there's no damping associated with this kind of system. Actually, it's an ideal system. In a real, we can't find this kind of system in real world, because it is a every system associated with certain damping method. It's an ideal situation. There's no damping. The damping is there's no damping. So then the free vibration means after giving initial energy transfer activity, that means initial disturbance. This is called initial disturbance to the system. There's no further energy transferring activity. There's no energy given to the system further, or energy taken out from the system. System vibrates freely without any energy transferring activity, called the free vibration. Then damping. So damping, what is meant by the damping? Damping means energy dissipating method. Every vibrating system associated with energy dissipation method. So we can categorize these energy dissipation methods, that means the damping method, in three categories, called the viscous damping, friction damping, and hysteretic damping. The friction damping, the energy dissipated due to the rubbing action in between the two surfaces, called the viscous friction damping. Then the viscous damping, energy dissipated due to the viscous friction called the viscous damping. Hysteretic damping, in simply we can say, due to the deformation of the material, certain energy is consumed for this deformation of the material. That means the existing bond in the material break and new bonds are formed. Then each cyclic deformation, this is happened, so there is certain energy consumed to break the bond and to form the bond, called the hysteretic damping. These three things we discussed in detail about in last class. Today we are going to move to the free vibration with viscous damping. That means you can represent the system like this. This is the mass. Actually, the last class I explained this vibration occurs due to the energy transferring in between the potential energy to the kinetic energy. Most of the situation there should be a stiffness to store the potential energy, there should be a mass to store the kinetic energy. The potential energy, some situation that it is stored in the body, or the potential energy may be stored in the gravitational form, gravitational potential energy also. So then this is how the viscous damping dashpot we are representing. This is called the dashpot. The viscous damper we are representing like this. Viscous damper. This is the K spring. The amount of damping is represented by the coefficient called C, called the damping coefficient. C is called damping coefficient. Damping coefficient. That is depend on the that is a property of this viscous damper. That means the dashpot. That is also depend on the fluid used inside this viscous damper. That is also depend on the surface velocity of the moving body. These things that is also depend. That means the force against the viscous friction force. Viscous friction force we can represent F is equal C x dot. If this is moving with the x dot velocity, viscous friction force we can represent produced by the viscous damper with having the C damping coefficient, we can represent by F is equal C x dot. F is equal C x dot. So then what is the unit for the C? This is Newton. This is C x dot velocity, meter per second. So that the new unit for the damping coefficient is equal Newton second per meter. Newton second per meter. Okay. Then in this situation, to start the vibration, we are given certain energy initially. Okay, energy to the system. Then by taking this energy, that means we are giving the two method to, we can give the energy as the form of potential energy, as the form of kinetic energy. That means we can give certain velocity to the mass, one of the method. Then another method is other method is by compressing this spring we can release. Okay, that means the two method to give the energy, the kinetic energy as the form of kinetic energy, as the form of potential energy. Okay, then after giving the initial disturbance, this is called the initial disturbance. No any further disturbance in free vibration. Okay, vibration, the system vibrate freely, but the energy system, the initial given energies dissipate because of the viscous damper, because certain energies consumed to do work against the viscous friction force. Okay, that's how the energy dissipate from the system energy dissipate. In this situation, let's see how this kind of system behave with the different input to the system. Okay, then let's obtain the characteristic equation, for this kind of system. Okay, let's move to obtain the characteristic equation for this system. Okay. Okay, we are going to obtain the characteristic equation for this vibration. Let's take the system. This is the system we are going to consider. A mass and the spring and the dashpot. The spring coefficient, the K, the dashpot coefficient is Z. Okay. Then let's take this is the position for the static situation, static condition. Then I will draw the initial length of the spring also. Let's take this is the initial length of the spring before compressing this. Let's take the initial length of the spring as let's take the y dash. Yeah. Then now it is compressed to a y. Then for this system, let's take we are given certain energy. Then system start vibration. Okay, system produce vibration. Then let's take the certain situation. Let's take the this is the level we are going to measure the distance from a equilibrium position. Then let's take the certain situation in vibration. The this mass is displaced from x distance from the equilibrium position, x, and the velocity x dot, it is moving in downward direction. So with the acceleration x double dot m. Then you can see the spring is compressed. Then the dashpot. Okay, this is moving downward direction. Okay, in vibration. Okay, then we are going to apply the Newton's second law concerning the motion of considering the motion of consider the motion of m mass, the applying F is equal ma to the downward direction. Okay, F is equal ma to the downward direction we are going to apply. So then what are the forces acting in downward direction? For this m mass, consider the m mass, what are the forces acting in downward direction? For the m mass, so gravity, mg, so gravity. Then here you can see the spring repulsion, the force generated by the spring, that is equal to K into total compression of the spring. What is the total compression of the spring? Here you can see the static condition. Static condition, what is the compression? Y dash minus y. Then further it is compressed by x distance, no? X distance. Further it is compressed by x distance. So that we can write plus x. Then when this is moving in a downward direction with the x dot velocity, what is the viscous friction force generated by the dashpot? That is equal to cx dot. This is equal to mx double dot. Okay, F is equal ma. Then we can further simplify this equation. The minus k y dash minus y minus kx minus cx dot is equal mx double dot. Okay, mx double dot. Here you can see these two is equal, no? The mg into k y minus y dash, that is these two are equal, no? Consider the equilibrium of in this situation. Consider the static equilibrium. Consider the static equilibrium in this situation. These two equations are these two values are equal, no? Then we can cut these values. So then we are having the equation the 0 is equal mx double dot plus plus cx dot plus kx is equal 0. Then we can develop further, we can simplify this equation. So I am going to divide all the entire equation by the m. x double dot plus c divided by m plus k divided by m into x. Okay. Okay, this is the equation we got. Then I am going to introduce a new parameter also. So what is the equation we got? 0 is equal the equation x double dot plus c divided by m. There should be a x dot in here, sorry, plus k divided by m into x. This is the equation we got. In here, for the k divided by m, for the k divided by m, we can put the k divided by m, we can put the omega n square. Okay, the k divided by m, we can put the omega n square. That means the free vibration without damping situation, the system natural frequency is called omega n. Okay, omega n. Then I am going to introduce another important parameter called theta. This is a new parameter called damping ratio. Okay, new parameter. This new parameter is equal. This is equal 2 theta omega n is equal z. C divided by c divided by m. This is the relationship between the c and omega n and c. Then if we make the theta into subject, theta is equal c divided by 2 omega n m. Okay, this is the definition of the damping ratio. Actually, you can see if the damping coefficient is higher, theta also higher. Okay, if damping coefficient is higher, the theta also higher. That means if the, for example, if dashpot viscosity is high, theta also goes high. Okay, then whatever the system natural frequency is low, again the damping ratio goes high. If mass is small, again the damping ratio goes high. Okay, the important relationship in between actually in when doing the solving the problem, the important relationship between the c and the theta. Okay, c and the theta. If c increases, c mean actually the dashpot damping coefficient increases, the theta also increases, damping ratio also increases. Okay, don't confuse these two parameters. The c is called damping coefficient, the theta is called damping ratio. Okay, damping ratio. Okay, then this newly introduced parameter I am going to put in this equation, this differential equation. Then we have this differential equation in the format like this: x double dot plus, for the c divided by m I am going to put the 2 theta omega n into x dot plus omega n square into x. This is the equation, the final equation we are having. Okay, in this equation you can see the I will write in the well-known format, the d2 into x into dt square plus 2 theta omega n into dx over dt plus omega n square into x. You can see it is a second order ordinary homogeneous constant coefficient type differential equation. Constant coefficient type differential equation called second order Why the second order? The highest derivative is the 2. That's why it's called second order ordinary. Ordinary differential. It is not a partial differential equation. It's a ordinary differential equation. The homogeneous this is equal to 0, that's why it become homogeneous. If there's a function it's not non-homogeneous, become non-homogeneous. Linear, it's also linear. Linear means there's no that means dependent variables and its derivatives are the degree of 1, or the derivatives and derivatives are degree of 1. That's why it's this is the degree of 1, this is also degree of 1, this is also degree of 1. That's why it's called the linear. With differential equation, equation with constant coefficients. Okay, second order ordinary homogeneous linear differential equation with constant coefficient, because you can see all these are the constant coefficients. The second order highest derivative is 2. The ordinary differential equation is not a partial differential equation. The homogeneous, this part is equal to 0. If there's no function of x, it's a linear. It's a order of every dependent variables and its derivatives are equal to 1. The differential with the constant coefficient, we are having the constant in front of the derivative terms. That's why it's become constant coefficient. Then I think you all familiar with this solving the differential equation because you are doing the maths lectures. Then you are in the maths module also. So I think you all more familiar with this solving the differential equation. Then how to solve this differential equation? Okay, let me summarize how to solve this differential equation. So then the solution of this differential equation can be written in the form xt is equal a e lambda t. This is the one of the possible trial solution for this differential equation. Okay, one of the possible trial solution for this differential equation. That means this differential equation we can satisfy from this solution. Okay, xt is equal a e lambda t, one of the possible solution for this differential equation. Okay, then here the a and lambda are the constants. A and lambda are constants. Okay, a and lambda are constants. Then if this is a solution of this differential equation, this differential equation should be able to satisfy from this solution. Okay, so then I am going to satisfy this equation from its solution. Here xt is equal a e lambda t. Then x dot t. What is x dot t? What is the derivative of this term? A lambda e lambda t. X double dot t. What is x double dot t for this the second derivative? A lambda square e lambda t. Then these 3 and 2 and 3, these 3 I am going to put in this differential equation. I am going to put this in this differential equation. Then we are having 0 is equal the d2 x double dot a lambda square e lambda t plus 2 theta omega n into x dot What is x dot? A lambda e lambda t plus then omega n square x a e lambda t. Okay. Then common term we can take it out from the solution. Common terms a e lambda t. You can take it out from these are common terms. Then we are remaining here the lambda square plus 2 theta omega n into lambda. Okay, the lambda plus omega n square. Okay, then here you can see the multiplication of two term become 0. Multiplication of two term becomes 0. So that means multiplication of this term and multiplication of this term is equal to 0. But it means the one of this term should be equal to 0. But I mean, if this is equal to 0, then our xt is also equal to 0. That cannot be equal to 0. So that this one should be equal to 0. So then we are having then lambda square plus 2 theta omega n into lambda plus omega n should be equal to 0. Okay, should be equal to 0. Here you can see the quadratic equation of lambda. Okay, then what is the solution of this quadratic equation? What is the solution of this quadratic equation? Okay, what is the equation we got? The equation we got 0 is equal lambda square plus 2 zeta omega n into lambda plus omega n square is equal to 0. Okay, see the quadratic equation we are having. Then we are going to find the solution of this differential equation to find the lambda for the lambda value, because here we are having the two lambda values. The two lambda values we can write in this equation. Lambda 1 comma lambda 2 is equal, what is the equation solution equation for this quadratic equation? Minus b plus or minus inside b square minus 4ac divided by 2a. I am going to use that equation. You all familiar with this equation. Minus b 2 theta omega n plus so minus b square inside square root minus b square 4 theta square omega n square minus 4ac 4 omega n square divided by 2a. That means the 2. Okay, that means the 2. Then lambda 1 and lambda 2, the plus and minus 2 distinct the two roots were in lambda 1 comma lambda 2 is equal. Further we can simplify this equation. We can we can 2 we can cut. Then lambda 2 we can cut the omega n, we can take it out from this square root sign, and also we can take it out from the here. Then we are having the minus theta, the plus so minus theta square minus 1 inside the square root. Okay, then lambda 1 and lambda 2. That means I will write the two solutions also. Then lambda 1 is equal lambda 1 and lambda 2. Then here you can see, according to this delta, according to this inside the square root value. If according to this value, that is called delta. You already know this delta is equal to 0. What happened? We are having only one real root. If delta is greater than 1, we are having two distinct real root. If delta is less than 1, we are having greater than 0. Greater than 0, we are having the two distinct real roots. If delta is less than 0, we are having imaginary roots, two distinct imaginary root. Then what happens if delta is equal to 0? Mean what it means? What in which situation the delta is equal to 0? This inside the square root term is equal to 0 mean if only in zeta is equal to 1. What happens? Delta is equal to 0. Then we are having two distinct real roots. Okay, in this situation we are having two distinct real roots. Okay. Then what happens if this term is equal to 0? The two distinct the roots are coinciding. If theta is equal, the roots are coinciding. The theta is equal 1. We are having the roots are coinciding. And real roots. Okay, real roots we are having, but roots are coinciding. Then what happens if theta is greater than 1 situation? Theta is greater than 1 situation, that means delta is greater than 0. Delta is greater than 0. Okay, delta is greater than 0 means this to become delta is greater than 0, the theta should be greater than 1. In that situation only delta is greater than 0. So then what happened? We are having the two distinct real root. Two distinct real roots. Then what happened if theta is less than 1? If theta is less than 1, we are inside this square root, we are having the negative. That means we are having the imaginary roots. Okay, two imaginary roots. Then here you can see here we are going to find the lambda to find the solution for the differential equation. That means I will explain. Here we are going to find the solution for this differential equation. Then we took the trial solution as this function. The lambda is a coefficient. When we are going to substitute this when satisfying this equation, for the lambda we are having the three different cases depending on the theta value. Okay, for the theta is equal 1, we are having the roots are coinciding. For the lambda and lambda 1 is equal lambda 2, only one real root. Then if theta is damping ratio is greater than 1, we are having the two distinct real roots. Then theta is less than 1, we are having imaginary roots for the lambda and lambda 2. You can see the three different situations depending on the theta value. Okay, depending on the theta value, we have to consider the three different situations for our solution for the differential equation. Okay, first I am going to consider one of these situation. Let's consider the situation Okay, let's consider this situation. We are having the two distinct real roots. Okay, first we are going to consider that one. Okay, let's take the situation. The first situation we are going to discuss, theta is greater than 1 situation. Theta is greater than 1 situation. What happened? We are having the two distinct real roots. What are the two distinct real roots? What are the two distinct real roots? What are the two distinct real roots? Lambda 1 is equal omega n minus theta plus theta square minus 1 square root. Lambda 2 is equal omega n minus theta, sorry, this is minus theta square minus 1 square root. Okay, here lambda 1 and lambda 2, that means we have the two independent solutions. X1 is x1t. We can write this two independent solution as in this way: a e lambda 1 t. Then the x2, another independent solution, x2t is equal b e lambda 2t. Okay, for the differential equation, we have the two independent solutions, x1t and x2t. So then if this is if we are having the two independent solution, we can write the total solution, we can write the complete solution as the linear combination of these independent solutions. That means the linear combination of these differential equations, a, b and c, a, e lambda 1 t plus, let's take this is a, b, c, d, db e lambda 2 t. Okay, for the linear combination of two independent solutions. So one of the property of differential equation solutions. So then xt is equal, so for the multiplication of ca, I am going to put the one simple constant a. E lambda 1, what is lambda 1? I will write that lambda 1 also. Omega n minus theta plus theta square minus 1 inside the square root into t, plus for db I am going to put the b e lambda 2 omega n minus theta minus theta square minus 1 square root into t. Then this is the solution, is the solution of that characteristic equation of vibration, is the solution. Okay, this is the solution. Okay, this is the solution. So then what is the solution of actually what is the solution that let me elaborate this solution. What is the form of this solution? Actually, what is this solution format? What is this solution format? Here you can see the minus, then here theta square minus 1, but here this term is plus, but when it subtract from the theta, this entire term, the entire coefficient become minus. This is like a e to the power of minus ax type. Here also the two terms are minus, it's also like minus bx term. So actually what is the shape of this curve, if we take this entire curve, what is the shape of this curve? Minus exponential curve, the t, the variable is the t. So if the t cannot equal to negative, if the t cannot goes to negative, so minus exponential, it having this kind of shape. Okay, both these independent, the two different terms having this kind of shape. Okay, then what happened? The addition of these two also form the same shape. Then finally, for the xt we are having this kind of shape. T xt. For the xt we are having this kind of term. Okay, this then what it means, I will explain this one. Then what happened, let's take this is equilibrium position of a certain system. Let's take the system is something like this in a static condition. Okay, then if we extend this spring up to this level, we have taken this given this kind of input to the system, then we stretch up to this level. Let's take the dashboard. Then what happens if we release from this position? If we release from this position, it follows this path. It follows this path. I mean, with the time, the displacement is equal to, if we measure the displacement from here, let's take xt. We are going to measure the displacement from here. If this is positive, this is how the xt is varying. It goes to 0 at the when the time goes to infinity. When the time goes to infinity, the xt goes to 0. This is how the system behaves. I mean, if we stretch this m mass to this kind of position, then if we release, what happens? If follow this curve. Okay, follow this curve. This situation is called, this is one of the situation this situation is called overdamped situation. Overdamped situation, because damping is heavy. Because the overdamp, why is called overdamp? The damping is heavy. Heavy damping is introduced to the system. The damping is heavy. That's why it's called the overdamp. It's take a longer time to reach to the equilibrium position. Actually, it's take the infinite time. The time is infinite. At the infinity, it goes to 0. This is the first situation. How the system behave in theta is greater than 1 situation. Damping ratio is greater than 1 situation. This is how the system behave. Okay. Then let's take the next situation. The theta is equal to 1. Theta is equal to 1 situation. Let's take the next situation, second condition. The theta is equal 1. Theta is equal 1. Then what happens if the theta is equal 1? What happens if the theta is equal 1? Theta is equal 1. let me take the two equations, so previous equations. Then what happen if theta is equal 1? What happen the theta is equal 1, this one. For the theta is equal 1, if this term is equal to 1, what happen? This inside is square root become 0. So then for the lambda 1 and lambda 2 we are having the lambda 1 and lambda 2 we are having the for both minus theta omega n. That means the roots are coinciding, and also we are having the real roots with coinciding. That means lambda 1 and lambda 2 are equal the minus theta omega n. These are the two real roots. Then so one of the we can write one solution as x1 t using this solution a e minus theta omega n t. Okay. Then in this situation we can write another independent solution using the method of reduction of order. I think you will familiar with this solving the differential equation. Using the reduction of order method, we can write the second solution from this kind of format. x2 t is equal, let's take the b is a constant, a and b are constants, the t, the variable t e minus theta omega n into t. Then we are having the two the independent solution. The second independent solution we are obtaining from the reduction of order method. If you are not familiar with this, please search on the reduction of order method. And then we have the two independent solution. In this situation also we can write the total solution by combination of these two independent solutions. xt is equal c by multiplying by c a e minus theta omega n t plus d b t into e minus theta omega n t. The linear combination of two independent solution, also a solution of the differential equation. I think you will know. Then we can further simplify this equation. xt is equal xt we can write by putting I'm going to take the constant a e minus theta omega n into t plus for the b t e minus theta omega n into t. So then we can further write this equation xt. We can further simplify this equation e minus theta omega n into t a plus b t. Then this is the equation of motion where when the situation the theta is equal 1 situation. This is how the system behave. The theta is equal 1 situation. So what is the behavior? What is the function of this format of this function? You can see the negative exponential function. That means it having this kind of curve. So then this is the linear curve like this. Okay, like this. T for this term. So then the multiplication of this term gives this kind of shape. The multiplication. This is not addition. This is multiplication. Gives this kind of shape. Okay. This is xt. This is t. Okay, multiplication system. So now I will elaborate this solution also again. Then let me explain this one. Okay, then we are having this kind of a solution. That means actually this situation is called critical damping situation. This is T, this is xt. Then this is how it behave. Okay, goes to infinity, goes to infinity. This is called a critical damping situation. Critical damping situation. Critical damping situation. Why it's called critical damping? Damp system have the smallest damping required for the aperiodic motion. Aperiodic motion. That means this is the in the critical damping. Critical damp system have the smallest damping required for the aperiodic motion. That means critically damped system have the smallest damping required for aperiodic motion. Aperiodic motion, that means no periodic motion. That means this is not goes to negative side. In aperiodic motion, this is not goes to negative side and comes to positive side. So it's called the aperiodic motion. Okay, then here let me explain this one using this diagram. Previously I used diagram. This is, let's take the certain equilibrium position for the certain vibrating system, viscous damping system. This is the spring, this is the viscous damper. Then if you take the system to this kind of position, let's take the position M. Then if you release from this position, the system reaches to the x is equal 0 following this curve. Okay, following this curve, it never goes to negative side. When theta is equal to 1, called the aperiodic motion. Okay, aperiodic motion. Then it not produce the overshoot. That means it not goes to negative side of the x. Then this is how the critical damp situation. This the second situation, how the system behave in theta is equal 1. You can see that depending on the theta value, the system behavior change. Depending on the theta value, system behavior is change. The theta is very important parameter. That means according to the by reading the value of the theta, we can predict the system behavior. That is why the system theta is very important for the damping vibrating system. Okay, then we are going to discuss the third situation. What is this third situation? What is that third situation? The theta is equal, it is less than 1. Okay, third situation we are going to discuss. Theta is less than 1. Then what happens? The theta is less than 1. For the quadratic equation, we are having the two distinct imaginary roots. Okay, two distinct imaginary roots. So what are the roots we are having? Lambda 1 and lambda 2 is equal the omega n minus theta plus or minus theta square minus 1 square root. Okay, then what happens if theta is less than 1, for this term we are having the negative value. That means this become imaginary. So that means I am going to, for the, in this case I am going to write this expression theta is equal -1 inside the square root, because it is inside it is negative, because it is inside is negative. I am going to take the -1 out from the square root sign. So then I can write 1 minus theta square root. Now it's become positive inside. So then we can write in simply the JOI, we can use 1 minus theta square. Then further I am going to simplify this equation term, j into gamma. The gamma means this term. Okay, gamma means this term. In this situation we are having for using the lambda, I'm going using the gamma, I'm going to write these two solutions. The lambda 1 is equal omega n minus theta plus j gamma. First lambda 1, then the lambda 2, we can write lambda 2 is equal omega n minus theta minus j gamma. Okay, then the solution, we can write this solution the same as in first condition situation, AE lambda 1 t plus BE lambda 2 t. That means the linear combination of these independent solutions. We have the two independent solutions but imaginary, but this solution we can write the linear combination of these solutions. So then I will write this entire solution. Next is equal AE lambda 1, what is lambda 1? Omega n minus theta plus j gamma into t plus BE lambda 2 omega n minus theta minus j gamma into t. Okay, this is the solution we are having. Then we can further simplify this equation. We can further simplify this equation using the Euler equations, using Euler formulas, equations. So what are the Euler equations? The exponential functions we can write using the trigonometric function. EIX we can write cos x plus I sin x. E minus IX is equal cos x minus I sin x. I think you will learn this equation in your A level. I think you are familiar with these equations. Okay, then call the Euler equations. I am going to write this expression, the complex exponential term using the cosine signs. Okay, we are going to convert. Before going to convert this equation, we can simplify this equation. That means xt we can write by taking the e minus theta. I am going to take this term out. Sorry, e minus theta omega n t, I am going to take it out from the entire expression. So then we are having AE here j gamma omega n t. In here we are having plus b e minus j gamma omega n t. Okay, then for this exponential term, I am going to write using the Euler's equations. I'm going to convert into a trigonometric equation using the Euler's formula. Okay. Then it's t is equal e minus theta omega n t. Here a what is e j gamma omega n t according to this Euler equations. We can write cos gamma omega n t plus j sin omega n gamma t. Okay, gamma n t plus b. For this term we are going to use this Euler formula, cos gamma n t minus j sin omega n gamma t. Okay. Then this is the equation we can write using the Euler's formula. Then we can further simplify this equation. Yeah. xt is equal e minus theta omega n t. Here you can see this term, addition of these two terms, the a plus b into cos gamma omega n t plus a minus b j sin gamma omega n t. Okay, in this equation finally we are having this equation for the xt. Xt is equal e, finally we can write in this format. In this equation the xt should be a real value. Xt is a distance from a certain reference plane. Is a distance. It should be a real value. So but in here there's a imaginary part, so that there should no imaginary term for the xt. So according to give the to produce the real value, a and b constant have to reside. Actually the a and b constant should be a complex conjugate numbers. So that means if a is equal in the format a plus bi, the b should be a minus bi. So that kind of constants are possible. So then what happen if a is equal a plus this kind of complex conjugate numbers. So I am going to substitute in this complex conjugate numbers in this equation. Let me show how these become real value. The e minus theta omega n t. Then a plus b. What is a plus b? A plus b, that means the 2a cos gamma omega n t plus a minus b. A minus b means 2bi 2bi yeah, a minus b, no? Yeah. Then j into sin gamma omega n t. Then here you can see the multiplication of I and j, that means minus 1. So then minus 2b. So I put the plus and minus 2b sin gamma omega n t. That means that 2a cos gamma omega n t. Then you can see for the xt we are having omega n t xt. You can see now the xt having the real value. If you take the a and b, for the a and b, if you take the complex conjugate numbers for the xt, we are having the real value. So then we can further simplify this equation. Let me take for the xt is equal e minus theta omega n into t. Let me take constant a1 cos gamma omega n t plus for a2, let's take a2 sin gamma omega n t. Okay, then further we can simplify this equation. X t is equal e minus theta omega n into t, the a1 square plus a2 square, then a1 divided by a1 square plus a2 square root cos gamma omega n t plus a2 divided by a1 square plus a2 square root sin gamma omega n t. Okay, then if you take this is I'm going to put for this one sin 5, here the cos 5. Okay, I think you all familiar with these calculations. For this term, let's take the k. xt we can write k into e minus theta omega n t sin 5 cos gamma omega n t plus cos 5 sin gamma omega n t. So we can add this equation. Finally we are having this equation xt is equal k e minus theta omega n t into sin gamma omega n t plus 5. Then this is the final solution we are getting for the situation where the theta is less than 1 for the viscous damping system with the free vibration. Okay, then what is the format of this equation? Let me take the format of this equation. This one should be, then oh, it's okay, no? Now it's okay. Okay. Then what is the solution of this kind of shape? What is the function of this shape? Okay. Then what is the function of this shape? You can see the multiplication of two term. The one is the exponential, negative exponential function. Then other one is the phase shift sine function. So what is the shape of this curve? Okay, I will write the function. Xt is equal ke minus theta omega n into t into sin omega n gamma into t plus 5. Okay, then what is the shape of this curve? So if you take this curve, the first term, the negative exponential term, we are having a negative curve like this. Okay, multiply with phase shift sine function. What is the phase shift sine function? Something like this, no? So for the phase shift, this for this function, circular frequency is equal omega and gamma. Omega and gamma. This is the circular frequency. I think you all are familiar with this kind of function. We already discussed this one. That means this is the circular frequency for this kind of vibration. This frequency is called frequency is called damped circular frequency. That means omega d called damped circular frequency. Okay, damped circular frequency. That means omega d is equal. Omega and gamma. But it means gamma term. We introduce the gamma term. The omega n 1 minus theta square root. Okay. Then if this is then the multiplication of these two terms, how we can represent graphically? T term, the multiplication of these two terms. So this is the Ke minus theta omega n t. So then we are having this sine function inside it. Then if we multiply this, finally we are having this kind of shape. Okay, something like this. The periodic time should be uniform, but okay. But it means, if we elaborate this one, but it means if we take the system to this kind of position, if we take the system to this kind of position and release, okay, I'm going to take this system which was in equilibrium position somewhere in here. If you take this system to this kind of position, then if you release, so what happens? It goes on this forming this kind of function for the xt. It goes to negative side of the function or negative side of the xt, and also it produces the periodic motion. Okay, periodic motion produce the overshoot also. So then this periodic time is determined by the sine function periodic time. The score tau d is equal 2π divided by damped circular frequency omega d, that is equal 2π divided by omega n 1 minus theta square. This is the periodic time of the damped vibration. This is tau d. This length is equal tau d. It is called the periodic time for this vibration. Periodic time for this vibration. You can see this in this situation, amplitude of vibration is gradually diminished. Here this is the first one. Then you can see the gradually it is diminished to the 0. It goes to 0. Okay, it goes to 0. At the infinity it goes to 0. Then you can see the gradually it is diminished. That means with the dissipation of energy, system energy, the amplitude of vibration gradually diminished to a 0. This is the three different situation depending on the theta value. If series less than 1 situation, you can see this system vibrate forming this kind of curve. Then if C dash is equal 1, they call the critical damping situation. Critical damp situation. In critical damp situation, it comes to 0 with the minimum time. Critical damping situation. Then over damp situation, we discuss this is called under damp situation. This is called under damp situation. Under damp situations. Okay, this is all about today's lecture. The next day lecture we are focusing to do some example problems regarding this theory part. Okay, then we are going to move to the logarithmic decrement in this vibration. Okay, let's continue next day class. Thank you.